cut over. We got pyrotechnics. It's very exciting. So yeah, I know I'm in the right room because Marius and BJ are both talking about debugging and everything going wrong, which is definitely, that seems to be the room that I can't get out of in my career. So that is the room I'm always in part because things keep going wrong. So I mentioned we did work for Joyent. We were bought by Samsung 2 years ago. And the reason that Samsung bought us is because we have an object storage service and they have an object storage bill that was rather high. And they wanted to use our object storage service. And so we have endured over the last several years. We've endured something that Samsung affectionately or not calls Samsung scale, which is a really, really, really big scale. And one thing I've come to appreciate is, we like to talk about how these microservice architectures scale, but unless you've endured one that hasn't scaled, you don't scale. Right, you just don't have a level of load where your lack of scalability has become viscerally apparent to you. So the whole like, I'm just gonna spin some more up. It's like, okay, well, have you actually done that? Like, that's great. Okay, so describe for me where you've actually done that. And this is where you kind of get to like, people kind of create this mythology about their own scalability. I think, maybe I'm being just too cynical, or I'm like, we're idiots, which is also a total possibility. And we're the only ones that have struggled with this. Because what we saw when we got to Samsung scale, is, well, I should say, when they were actually doing like their due diligence, they wanted to like do some really serious tests, and Manta at the time was just not that big. But we didn't want to tell them how many physical computers it was on because it wasn't a big number. But it was a distributed system and it was designed to scale for sure. And I'm sure it would scale. I just don't want to tell you how many computers it's on because then you'd be like, wait a minute, what? But they wanted to put a level of load that was like not going. Like, we needed a lot more computers than that. Like, we need some more hardware. And I think we were frank with them. I think we're like, well, listen, we can't do this because we're going to need a lot more hardware. And they're like, oh, great. Well, we'll get you a bunch of hardware. So they made a bunch of hardware show up. It's like, all right, bluff called. Thank you. Shit. And it had the bonus of being incredibly shitty hardware, which is, they pulled it out of a dumpster somewhere. So which is always a bonus. May all your hardware be shitty because you discover all sorts of pathologies that you didn't know existed in your stack. And we, in particular, we had a router that liked to play where are the routes game, where it would just be like, you know what? You guys seem cool. I'm just gonna like shuffle everyone's routes for a little bit. I'm gonna disappear for a little bit. And like, distributed systems don't do well when literally no one can talk to anyone else for like a minute. And then it's like, why did it take you so long to recover? It's like, it's a miracle that it recovered at all. Anyway, so we got kind of past that. And in doing that, we did discover some of those kind of sunny day scalability problems. Like, it was so great. I remember there was one component and we only had we had a small number of these deployed and it didn't scale. And we could see from our instrumentation that, wow, this service is taking a long time. Oh, it's CPU bound. That's so nice. Let's create some more. And then that wasn't the scalability problem. That was great. That was so great. And I should have held on to that moment for a lot longer, because when that happens, I feel like that's the exception to the rule. I feel like what is much more common is like, oh, we scaled out a bunch of these and now the problem is even worse. And like, what's going on? And it's like, what's going on is you're getting God's own back pressure. That if you do not design back pressure into your system deliberately, God will put it in there for you, and you will find it. And so if you are seeing high latency outliers in your microservice architecture and you deploy a bunch more of them, the latency gets even worse. It's because there is something else that these things are talking to that is crushing you. And understanding that problem is challenging. And that's why Dapper, why Lightstep, why a lot of things, why open tracing, and how can I find but in our architecture, actually, finding the service was not necessarily the problem, because it's the data service. That I wish all services were stateless. Right? May all your services be stateless, but they're not stateless. And the statelessness, I mean, it's not a lie. It's just a luxury, right? It's a luxury. If your service is stateless, like, that's awesome. And like, you should live such a pampered first world existence where you can just like, no, I've got like this key value store service. And like, I just like call out to that thing like as frequently as I want. Meanwhile, that service is getting absolutely tortured because it's like, you have state in your system, I think, right? I think if you're entirely stateless, like, aren't you irrelevant if you're entirely, I don't know. But I mean, relevance is in that state, and that state has got to get to disk and got to come back from disk, be it solid state or be it actually spinning media. And that is where things get just awful. Absolutely awful. And that's like, oh, I'm just going to spin some more up. It's like, not really. No. This is an actual like database, like an actual database. And it's a database having a bad day or a bad week. And and in particular, we have been absolutely crushed by Postgres auto vacuum problems. And by the way, if you want to be victim blamed, just because like that's what you're into, tell a Postgres person that you're having an auto vacuum problem, and it will be explained to you why it is your problem. Like, you have created this problem. You brought this upon yourself because you have mistuned your system. It's like, oh no, there are all these like tunables you're not doing correctly. If you hire me as a consultant, I can explain what's going on. And then you realize you do this a couple of times, like, oh, thank God, like I can hire you as a consultant. You explain what's going on. You bring them in as a consultant, and they have got no fucking idea what's going on, and they go on to the next gig. You're like, wait a minute. Okay, Postgres is like a consultant factory, where we kind of come in with this like voodoo, and then we like hightail it before the latency, while the latency is still bad. Sorry, I don't mean to overly denigrate Postgres, but the problem is, and I think that all databases have, I think, we've been telling ourselves this anyway, have this problem at some level where there is asynchrony in the database that absolutely crushes latency. And what's going on and why? I mean, I understand, I get it, auto vacuuming, and I also get that like Postgres really wants to go home at 5 o'clock. I mean, this is like the kind of the core challenge with Postgres is Postgres was designed for a world where it's like everyone can go home, so I can clean up this galactic mess that I made during the day, and by the time people come back in the morning, it'll be fine. And that is Postgres's, that's its worldview. And it's like Postgres, you don't get to go home, and in fact, no one gets to go home. Like, we're all stuck here 24/7, 365, and I'm as sad about it as you are. Like, I want to go home too. And you're just getting absolutely annihilated. And when auto vacuuming is like this darkness that descends upon the land. And the system behaved much more pathologically than we thought it should. And it was very hard to figure out what is going on. Like, why are things so bad? Like, I get that they're bad, but why are they so bad? And we just had a very hard time understanding what these single systems were doing. I mean, it's embarrassing that I spent my entire career and I still don't know what the computer is doing. And I feel like I still have these very basic questions. And in particular, when the computer is doing something and it's actually doing work, it's on CPU, that's great. That's another luxury. Like, thank God. Because if you're on CPU, you're doing work, you can figure out, what are we doing? The problem is you're not on CPU. It's like everyone is just like standing around staring at everybody else. It's like, well, who's supposed to do the work around here? What's going on? And you get a system that is like everyone is frenetically staring at everyone else. And it's very tempting to begin to look at individual components and try to reason from individual components, but you're not really connecting the dots about what's going on. And what we found is that we would constantly go in and you naturally have to aggregate data to figure out what's going on. Like, okay, we're off CPU. Like, why are we off CPU? But you're going to aggregate to answer that question. And that's something we use DTrace a lot to do that. But when you aggregate, you throw out the temporal nature of the data. And what we found is like, we could aggregate and still not figure out what the fuck's going on, which is extremely frustrating. And I want to be able to visualize the system, and I want to be able to visualize this kind of temporal aspect of the system. And I want to be able to visualize the different entities in the system and be able to visualize them over time, be they processes or threads or CPUs or devices or IOs or whatever. I want to take each of these entities, because these entities have state, they progress through these states. What happens if we visualize it? So I spent some time being like, I'm going to get GNU plot to do this. We say GNU plot, right? Is it GNU plot? Don't fuck with me. All right, okay. I do say PDF, not PDF. So I guess I mean, I was just like, this is a totally like self-inconsistent position. But, and actually, I mean, you don't have to say SFIG. I just say SFIG. So that's what it is. All right, it's fine. It doesn't sound okay, but that's fine. And now of course I completely lost my train of thought. But so in terms of actually being able to visualize these things over time, and like GNU plot, I will beat you to death until you do this. And GNU plot won that battle, actually. I love GNU plot. GNU plot, I realized, is like, GNU plot is the tool that has been there my entire life. That's like when there were footsteps in the sand and there were only one, that's when GNU plot carried me. So I love GNU plot, and what I was doing to it was wrong, and I needed to stop doing it to it. And I'm like, all right, I'll write my own thing. And so, and enter Svig. So Svig is actually, I mean, is really interesting, right? Where you take like, it's an image, but it's actually like a program. So you can actually make these like images that actually have got a lot of computational work. And so I'm like, let's start and let's just visualize state over time. Let's do it for CPUs. And I'll, if I'm, is my screen is sharing. So, and this is a system that's like working like 30% of the time, CPU wise. And so I'm like, I don't know, what are we gonna see? What the fuck? Not that. Like, no, didn't mean like the AV's fine. Sorry. No, the AV, there's not an AV problem. But, yeah, oh my God. No, you're not supposed to. But this was not what I was expecting at all. So I don't know what I was expecting, but not this, which is, so what we're seeing here is we are seeing output where we're seeing visualization. This is over a 20-second period of time. So this is 20 seconds on a physical machine. And each one of these lines is a single CPU that is executing in time. And this is during like the hurdy time. This is when like all hands on deck, we want everybody working. And these guys are obviously not working most of the time. Like they are idle most of the time. That wasn't a surprise. We know that we're 70% idle. But one of the things I wanted to understand is what's happening in that sub-second. We look at this kind of percentage number in the second. I'm like, there's got to be a lot happening sub-second. It's not just sub-second. It's there is so much going on in here in terms of, I mean, clearly there's a lot of temporal-based activity in here, and we can kind of zoom in on this thing, and you can see that we've got these like gigantic towers here. And what is going on here? Like, what is this system doing? And we can kind of, let's go to one of these states here, like the user thread. So this is, the green is the user thread, and we can actually, like, let's see, for example, like what we're actually executing. So and how does this work, by the way? This works by gathering a huge amount of data off the system and then visualizing it separately. So there's a monster DTrace script that's pulling all this data out of the system, that's storing it into kind of stream JSON that a program is then rendering into a Svig that we're then playing around with. And so I can take one of these, I'm like, okay, so where is Postgres? And there are all of the Postgreses. It's like, okay, this is helpful to know because the Postgreses are like not doing work very frequently. There also clearly is, there's some time delineation here that's interesting. This box is running a ton of microservices and services that are around this thing. So if you wonder what the node is, those are all of and these are different node processes running. And we can kind of break it down in other ways and so on. But so, okay, this is interesting in that these striations are not what I would, again, what I'm expecting, but not necessarily that. So let's actually zoom out. You notice that when we zoom in, we kind of get over zoomed here because we just don't have, we're not presenting all of the data. So we can kind of crank another one of these, it's a little more zoomed in, and we can zoom in on a particular period and kind of begin to see what's going on there. And so there we go. And when I zoom in, you can see that I'm taking this period and kind of re-cranking it, going over the original data and re-cranking it, but now at much higher resolution. And you can see that the quality of resolution goes up a lot. So we can see, okay, now we can begin to see what's going on. But again, there are way more questions than answers from this. And I think that one of the things that, this is true of DTrace too, but this is not trying to give answers. This is trying to prompt questions. And one of the things about microservices is when you are, or any distributed architecture or any computing system, when you are debugging these things, you have to use your brain. There is not going to be a tool that gives you the answer. And there are tools that will tell you that you are sad. But you probably know you're sad. And there are tools that will help you identify where your sadness is coming from, but they're going to need to work with your brain to figure that out. And when you get to this level of debugging, this is going to prompt questions, not answers. So one of the things we looked at is like, all right, so let's go back to over this time, what is Postgres doing? So another kind of monster D script to instrument Postgres itself. Where is Postgres spending its time? All right, zoom, not now. Where is Postgres spending its time? And this is Postgres' state. Now, this is a totally different view. Each one of these rows is a Postgres process. doing the things that Postgres can do. And Postgres can be on CPU, that's the green, that basically never happens. We don't actually do any work on the CPU at all. We spend all of our time waiting. Like, okay, I think I knew that. Okay, that adds up, that's consistent. And here I'm off CPU waiting. I'm waiting for an incoming connection. That happens a little bit, but not that frequently. I'm off CPU on a semop. I'm off CPU on a semaphore operation. Okay, and we can see some lot of time where a Postgres process will be off CPU on a semaphore operation. And these are long periods of time. You look at this, and this is, this is like a second of waiting on a semaphore for a second. Why? Where are we? And we this is what we kind of knew through conventional tools that we think, oh, we've got a Postgres locking problem. And it's like, oh, don't worry, here's a consultant who will tell us how we have misdesigned our schema and why we have a locking problem, and then we'll run away before we actually resolve it, but taking a lot of our money. But so we thought, oh, this must be a locking problem, but it's not it at all, actually. If you look closely, and this is where I think that with some of these new visualizations, I just don't know, is this going to be something that's valuable or not? And this is the view where I'm like, actually, I think we're onto something. I think this actually is valuable, because you can see that all the Postgres processes are waiting on semaphore operation, except for this guy. And he's off CPU in IO write. And here, all of them are here except for a different person, a different Postgres process. Also, same state, off CPU during a write. And this is an example of a true needle in the haystack, because you have all of the Postgres processes are blocked on a semaphore that this thing owns. And it's off CPU. It is the needle in the haystack, off CPU, in CPU write, in IO write. And I'm like, why? What are we doing? Why are we off CPU in IO write? And then you're like, oh, right. So I go instrument the system a little better. And that's kind of zooming in on that. Actually, this is kind of, before I do that, this is kind of an interesting view where if you zoom in on this kind of muck, if you zoom in on this muck here, that is say get higher fidelity, you can see the same thing happening in the small over and over and over again. And these are not big units of time, right? This is, like one of these little towers of power here. This is that, so that span is 300 milliseconds. So, these are, 150, 200 milliseconds wide. Good luck finding that. And yet, it's happening over and over and over and over and over again. And if you aggregate that up, you aggregate it into meaninglessness. So, okay, so now another way to instrument the system. Okay, now we know it's, I want to know, why are we off CPU and IO write? Well, there are a couple of reasons we can go off CPU. And one of them is because we've actually been delayed by the file system. And the file system has a transaction delay. That's in that. So this is rerunning the same workload, but with now a different script that is explicitly calling out off CPU transaction delay versus off CPU because of ZFS write. And all of a sudden, and I'm sorry for the garish colors, the fluorescent green explodes. You don't see the blue anywhere. We are off CPU because we are being throttled by the file system. Because the writes, we are doing a bunch of async writes. Postgres is doing async writes all the time, right? It's doing these writes, and it's writing them to the commit log, and then it's going off and doing something else. But ZFS does apply back pressure. And ZFS is like, I'm falling behind here. And I actually can't keep up with the write traffic, so I'm going to throttle your writes. And again, this is a little bit of God's back pressure, where I'm just going to, I don't know, pick one of these things, like you're being throttled. Sorry, pal. And everyone behind it is being throttled behind it until those writes can catch up, which they do. Maybe 100 milliseconds later, they catch up and the throttle comes off. And then we're able to proceed for 100 milliseconds, and then we hit it again. So it was not actually, and to kind of zoom in on that, we again see this happening over and over and over and over again, and then happening for a particularly long time. This is when the transaction group is going out. But this is just an example of how I feel I understand nothing. I mean, the longer, I've been doing this for too goddamn long to be so surprised by, and this is like a workload that has existed for like a while. And this is not even like some newfangled distributed whatever. This is like a single system. And I find myself still incredibly surprised by what's actually going on. And I think that in our microservices architectures, we need to have the ability to really see them, to understand what is happening. Because too often we kind of cargo cult success, where we do something and this problem changes, so we like, that must have been it. It's like, maybe not. Who knows? And in this case, the auto vacuuming, the real problem with auto vacuuming, it is actually not the random reads, which is what we were fixated on the entire time, or the random reads. It is the writes that are, it's the async writes that are crushing us, because auto vacuuming has to rewrite every table, essentially. We're going to rewrite the database. And it is that those writes that, if it were not for the reads, would happen very quickly. Yes, this is on spindles. I know, I'm sorry. I'm like the last person on earth. It's like still running on my, I like my computing to be real retro. So I'm running like actually like rotating media, which is a terrible idea. And if you've got a lot of money, you should never use rotating media. But this is the world we're stuck in because of the cost. And trying to understand, how do we balance these systems? And I think there's a lot of surprising behavior like that. As you deploy your microservices, brace for those kind of surprises and build the ability to actually debug these systems, and do not be satisfied with what you think is the answer, because there's probably something much more ornate than you realize going on deep in the system, even in simple systems, which we think we understand. I know I went over, sorry, thank you.